Welcome to this video session. My name is Samuel Chukwu Emeka. In this video session, we shall discuss relations and functions. This is the first part of the video playlist. Relations and functions is a very broad topic. There are so much to learn concerning relations and functions. In this video, we shall kind of look at the introduction, know what a relation means, know what a function means. We shall know how to represent relations and functions, the various ways by which we can represent relations and functions. Then we shall know what variables mean. Then we shall look at the domain. Know what a domain means, know what range means, and know how to express them in set notations. Okay, let's look at some vocabulary words that we are going to encounter in this video session, just for this video session. We shall talk about variables. We shall talk about relation, talk about function, talk about representations of relations and functions. Relations and functions. Okay, in this case, we shall talk about a table, mapping, the vocabulary words here. We will talk about table, mapping, graph, ordered pair, and equation. 5 things we shall discuss under number 4. Then number 5, we talk about domain and range. And we kind of express the domain and range in set notation. Remember in the video on quadratic inequalities, we had to use interval notation. Here in this video, we shall use a set notation. So we shall learn how to write a symbol, okay? Let's begin with variables. Before, I was very fit, ready to go, like this, But after eating a cheeseburger, McDonald's cheeseburger, my cheeks, I now have big cheeks, big head, big stomach. So, in fact, I've actually reduced now. But you see that the more I ate the cheeseburger, the more weight I added, So let's say now we have 2 variables. We have the weight. The weight, let's say, is W. Okay, I added weight because of the burgers. Let's say is B. So you see, let's say we are doing a research. Let's say we are doing a research, or you are doing a research on how many pounds someone gains, like what is the weight of someone if he eats burger. You want to know the effect of eating burgers on the weight of people. This is just an example, okay? Those restaurants that produce burgers, don't be mad at me, please. I am just giving an example. When they see this big stomach, they think it's beer, they think it's Heineken, or Budweiser, or Bud Light. It is not alcohol. It is burgers that produce this beer, that produce this big stomach. Burgers and sodas, I am cutting back on them now. But anyway, don't be mad at me. This is just teaching mathematics. I want to use an example. So let's say you want to write a grant. You want to do a research on the effect of burgers on pounds that people add, the weight that people gain. So maybe you find out, you kind of find out maybe that you have burgers, you have weight, that maybe when somebody eats, let's say, a burger, probably the person will gain, let's say, 3 pounds. If the person eats 2 burgers, maybe the person gains 6 pounds. If the person eats 3 burgers, the person gains 9 pounds. If the person eats 4 burgers, the person gains 12 pounds, and so on. Now, you can now establish a relation. Already you have established a relation here by writing the values of the burger and the weight that the person gets. Okay? And this relation can be written as B as an ordered pair. Where the burgers is the input. Okay? This is your input, and the weight you add is the output. So it can now be represented as an ordered pair. Now, these two things, the weight and the burgers, are what we call variables. We see that the weight depends on the burgers. So because we say that the weight depends on the burgers, the weight you gain depends on how many burgers you eat. So that means that weight is a function of burgers. Okay, we pronounce it as weight being a function of burgers. Just like in algebra and in calculus, you have it that y is the function of x. This is known as the function notation. Okay, y is f of x, or function of x. So you see that this way is a function of burgers. And you can now form an equation based on the same table that you have done. First of all, you have represented this relation as a table. Then you can also represent it as an ordered set. Okay, 1 and 3, comma, 2 and 6, comma, 3 and 9, comma, 4 and 12. Okay, you can represent it as an ordered set. And I'm going to show you how you can write this. When we start writing set notation, I'll show you how you can write this thing. It's called braces. We call it braces. Braces. It's on your keyboard. I'll show you how you can write it. Okay. Now, so you have seen now that you did some experiment. Maybe you sampled some individual when they eat 1 burger, he gains 3 pounds. When he eats 2 burgers, he gains 6 pounds. From there, you have already formed a relation, represented it as a table, represented it as an ordered set. Okay, you can also represent it as an equation or a rule. If you look at this now, we notice that W is equal to 3B. Okay, now this is an equation, which means you can also represent it as an equation. So this set of input and output, you have represented it as table, as another set, as an equation. You can also represent it as a mapping. Okay, we can represent it as a mapping or correspondence, whereby this is the B, this is the W. Okay, this is 3, 6, 9, 12. Map 1 to 3, map 2 to 6, map 3 to 9, map 4 to 12. You can represent it as a mapping. You can also graph it. You can represent it as a graph as well. This is what we call a relation. For each input, you have an output. It defines a relation. Okay? Any set of ordered pairs is what we call a relation. When you input 1 burger, you gain 3 pounds. You input 2 burgers, you gain 6 pounds. Input 3 burgers, you gain 9 pounds. Input 4 burgers, you gain 12 pounds. Any set of ordered pairs is a relation. So a relation is a set of other tests, which means for each input, you must have an output, period. Anything you do, you must have a result. Okay? Just like in philosophy, you can call it cause and effect. All right. Now, let's come back to calculus. Let's come back to calculus and algebra. We just gave an example of weight and burger. The W equal to 3B, okay? Here, we see that the weight is known as the dependent variable. Dependent variable. Why do we call it variable? Variable, vary. Okay, when you talk about variable, vary. Variable. Variability. Okay? Variation. So something that changes is not constant, it's a variable. Alright? So W will change depending on how many burgers you eat, your weight will change. Okay? Now, so W is known as dependent variable because it depends on how many burgers you eat. Then B is known as the independent variable. Independent variable. Now, why do we say it's independent variable? The burgers were just there in the restaurant. They didn't find me. I found them. I bought them. I ate them. And my stomach became big. So that is what we call that and I gained pounds, which means that my weight is dependent on the burgers that I ate. Okay? Now, another thing you can call this is basically what we call dependent variable and independent variable. You can also call this W as the output because it is the result, output or result. Right? And then the B is the input. The input, you eat the burger, then the weight is the output. The input is the burger you eat, your weight that you gain is the output that you display. Okay, let's go back to statistics. If we go to statistics, I'm trying to connect this topic with several topics that you might come in contact with. In statistics, this W, we can call it because it's the dependent variable, is the output. In statistics, you can call it the response variable. Response variable. Okay? And then the B, which is the input, you can say it is the explanatory variable. Explanatory variable. Or you can call it the predictor variable. Predictor variable. Why do we call it predictor variable? Because it is used to predict the response. How is this so? Because once I establish this equation, then of course from here I can now predict if somebody eats 10 burgers, I can predict the weight of that person, that the weight the person will gain. If I can predict now, this is now the predictor and this is the response. Okay? This is the predictor because you can use it to predict the response. Is that clear? So if somebody eats 10 burgers, I already know that the person will gain 30 pounds from this equation. Okay? That is statistics. You will see this in statistics. So this is applicable to y being a function of x. Because as we say here, w is a function of b. It's a linear function as you see it now. It's a linear function. So here, y being a function of x, this is known as the function notation. Function notation. Basically, this is what we shall be using. I just use this weight and burgers to, kind of explain to you how variables and relations work. So, y is a function of x. Y is the what? Dependent variable. It is the output. It is the result. It is the response variable. Okay? Then B, X. X is the what? Independent variable. It is the input, it is the explanatory variable, or the predictor variable. That is it. Okay? So that is basically what variables are about. Dependent variable, the two main variables we have are dependent variables and independent variables. And we already said that a relation is any set of ordered pairs, which means it's basically telling us that it's a set in which for every input you must have an output. Okay? For every input you must have an output. Alright, now what is a function? A function is a special kind of relation. A function is a relation also. Okay? All functions are relations. Now, but it's a special kind of relation in which for every input you have a unique output. Not just an output, but a unique output. What does this mean? What does it mean? It means that no input can have two different outputs. Okay? Let me explain this. Let me explain this, for instance. Okay? Now, assuming I have this relation, y equal to square root of x. All right. Let's map this x to y. Let's map x onto y. If I have, let's say I have 1, 4, 9, right? And I have negative 1, 1, negative 2, 2, negative 3, 3. Okay, look at this now, for instance. Square root of 1, right? It could be plus or minus 1. Remember, square root of 1 could be plus or minus 1, right? So, square root of 1 could be plus 1, or it could also be minus 1. This is what we call a mapping or correspondence, okay? A mapping or correspondence. You know, different ways by which you can represent relations and functions. Then square root of 4 could be 2 or negative 2. Square root of 9 could be 3 or negative 3. Now, this is a problem. This is not a function. Okay, it is a relation now. It is a relation. Why is it a relation? Because every input has an output. It is a relation. Okay, you have 1, negative 1. You have the relation, a set of ordered pairs, 1 and 1. Then you have 4, negative 2. Then 4 and 2. Then you have 9, negative 3. Then 9 and 3. Okay? So this is still a relation because it is a set of ordered pairs. It is. Every input has an output. But it is not a function because every input does not have a unique output. You see an input having two different outputs. It's not going to work. It's not going to be possible. Okay? It's just like when you take an exam, you get two different grades. Is it possible you take just one exam and you get two different grades? Is it possible? No. So imagine it like that. It's not going to work. Okay? Now, so a function in that case is a relation in which for each input there is a unique output. You can define a function that way. You can also define a function as a distinct set of ordered pairs or a distinct relation in which no input repeats. Okay, 1 shouldn't repeat, 4 shouldn't repeat, 9 shouldn't repeat. So you can define a function. You can also define a function as a relation in which there is a unique range value for each domain value. That will soon bring us to domain and range. I'm going to explain that in a minute. Okay, so in a function, it's a relation because every input will have an output. But it is a special kind of relation because no input will have two different outputs. Every input will have a unique output. Will have exactly one output. Okay, you can also say that every input will have exactly one output. Exactly one output. No input will have two different outputs. No. Alright? Now, remember that the relation is a set of ordered pairs, x, y, where x is the input, okay, and y is the output. Some textbooks will write this as first component, some textbooks will write it and they will write this as second component. It just means the same thing, input, output. Just like you do it in economics, you use input, output. Okay? You can also say first component, second component. It doesn't matter. Now, let us now talk about representation of relations and functions. So, as we have mentioned, while we were doing this video, you can represent relations and functions as another pair, x and y, which means input, output. You can represent relation and function as a mapping, or correspondence. Okay? You can map x onto y. Map x onto y. Okay, like we did. And you can, for every input here you have an output. A, B, C, D, E, F, G, H. You can represent relations and functions like this as a mapping. This is called a mapping or correspondence. I think we mentioned it earlier. You can also represent relations and functions. You can represent relations and functions also as a table. Remember the table we wrote about the weight and burger? We had the burger here and we had the weight. Okay? Here we can now have x and we can now have y. Okay? If y is equal to 3x, then this will be 0, 0, 1, 3, 2, 6, and the rest of them. You can represent relations and functions as a table. You can also represent relations and functions as a graph. Okay? I think that's the next chapter we will do. When you are drawing graphs, you have your x and you have your y. The x is the horizontal axis, the y is the vertical axis, and you have your scale, you have a suitable scale. Let's say 1 cm represents 1 unit on the x-axis, 1 cm represents 1 unit on the y-axis. Right? You can represent this as a graph. 0, 0, 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay? 1 when x is 1, y is 3. Okay? And when x is 2, y is 6. So you can represent it as also a graph. Then you can also represent relations and functions. The fifth way that you can represent relations and functions is as an equation. Or rule. We can say or a rule. Sometimes they ask you what is the rule of the function or what is the rule of the relation. Right? What I mean by that is y equal to, in this case, if this is that, then y equal to 3x. This is the equation or rule of the function. Alright? So we are going to look at these representations one at a time in subsequent videos. We are going to determine the domain. We are going to determine the domain and range of these. Domain and range from a table, domain and range from an equation, domain and range from a graph, domain and range from a set of ordered pairs, domain and range from a mapping. We are going to determine it. For this video, we shall focus on determining domain and range from a set of ordered pairs. There are questions here on the board. and also domain and range from a mapping. That is what we shall do in this video. Then other videos we shall talk about domain and range from an equation. That one students find problems, you know, some students find it difficult on that, domain and range from an equation. So now, what do we call domain and range? Simple. Domain is a set of all the input values, okay? So all the x values, domain is a set of all the input values, all the values of the input is what we know as the domain. The set is a set now, okay? And that brings us to point, assuming we say let domain be B. Let domain be B. So D is a set of all input values. Set of. Now, how do you might ask me, how do you draw these braces? Set of, you know? You've got to draw it well. You've got to draw it well. When I was learning this, I had to draw it. I had to, you know, when I was learning this, I had to know how to draw it. You know? And this is the way you can draw this. It means set of. Set of. It's called braces. It's on your keyboard. So what you need to do, you just do this. You just draw something like this. And then from here, you do like this. See that? Okay? The opening braces. And then the closing. All you need to do, you do like this. Right? And then you draw this. Let's do it again. Set off. Set off. Okay, you draw something like an integral sign. Just draw something like an integral sign. And then from here, right from here immediately, do something like this. Okay? And then closing, you do something like this. Right? And then right from here, you just do something like this. Yeah. But you must make sure that you write your domain as a set. If you're writing it in set notation, you have to write it well. If you use parentheses, it is wrong. You've got to use braces. Okay? These braces means set off. Set off. So domain is a set of all input values. And then let's say let range be R. Range is a set of all output values. All output values. Okay? Now, another thing I want to talk about is this. Y, you know that Y, we call it the response. Well, in statistics, we call it the response variable. Y is also the output. You can also call Y an image. Okay? You can also say that Y is an image. You can also say it's an image. Right? X is the element and Y is the image. X is the input, Y is the output. You can also say that. So range is a set of all output values, or all the second component of the ordered pair. The set of all second components of the ordered pair is the range. The set of all first components of the ordered pair is the domain. Okay, so that is domain, that is range. Right? Now, set notation is just representing it using braces. We're gonna represent a lot of things using set notation for this topic on relations and functions. Our domain and range, we will try to represent it using set notation. All right, let's go ahead and do some questions. The questions here says, determine whether each relation is a function, then find the domain and range of each relation. Okay, so question 1, we have set of 3, 2, 5, 1, 7, 8. Right? So we want to know whether this is, of course it's a relation. Why? Because every is a set of ordered pairs. It's a set of ordered pairs, okay? We can say that the image of 3 is 2, image of 5 is 1, image of 7 is 8. Or output of 3 is 2, output of 5 is 1, output of 7 is 8. All right. If you are giving this is, you know, as a set of ordered pairs. Now, if you ask me, I would just say this. When you're asked to do, when you're given this, right, and you're asked to determine whether it's domain or whether it's a function or not, and you're asked to determine the domain and range, you can do it straightforward, by looking at it, it's good. You can answer either way. That, of course, if you look at it, it is a function, because for each input, there is a unique output. There is exactly one output, right? And no two inputs, no input repeats itself. No inputs repeats itself, right? Remember, we can define function in 3 ways. Let me define it again in 3 ways. Number 1, a function is a special kind of relation in which for every first component or input in the ordered pair, there is a second component or output. Okay? Or you can define a function this way. A function is a special kind of relation in which no first component repeats itself, or no input repeats itself. No input repeats itself. Or you can also say this. A function is a special kind of relation in which there is an exactly one range value for each domain value. Okay? Domain values are the x values, range values are the y values. Alright, now domain values are the x values, which are the input values, and then range values are the y values or the output values. You can also say that domain is a set of all x values. Range is a set of all y values. So many definitions, huh? So if you look at it, you will say, of course, the relation is a function. Of course. Looking at it, you see that. No first component or no input repeats itself. Right? So the domain, let the domain be D, domain will be set up, right? 3, 5, 7, because they told us to determine the domain and the range. And then the range will be set up 2, 1, 8. Yeah. You can do it this way by looking at it. Now, for some of you that don't like looking things horizontally, some people don't like just looking things horizontally. They might get confused. Then just put this as a map, right? Put it as a mapping. Just put it as a mapping. Map it. Okay, x, y. Map x onto y. 3, 5, 7, 2, 1, 8. 3 maps to 2, 5 maps to 1, 7 maps to 8. You see, 1-to-1 function. 1-to-1 function. I didn't even mention that in there. Don't mind me. That's going to be in later videos. We shall talk about it. 1-to-1 and on-to functions. Okay, so you see that the domain is 3, 5, 7, and the range is set of 2, 1, 8. Remember, you must put it in set notation. You must. If you put this as parentheses, it is wrong. Domain is a set. Range is a set. Please note that. If you put parentheses, it is wrong. Okay? Question 2. Here, question 2, we have 7, -3, -5, 4, -3, -4, 7, 2. Okay, if you look at this now, you see that this is a relation. It's a relation. Why? Because it's a set of ordered pairs. Remember, a relation is any set of ordered pairs. But is it a function? No. Why? Because an input has 2 different outputs. An input has 2 different outputs. You look at it now, or you can say that an input repeats itself. It's not a function. Okay? It's not a function. And if we kind of want to map it, if we map it, we'll get something like this. 7, -5, -3. And this will be -3, 4, -4, 2. So 7 maps onto -3 and 7 maps onto 2. You see, this is wrong. Okay, you can't take the same. You can't take one test and have two different grades. You cannot. You can't take one test and have two different grades. So -5 maps onto 4, and -3 maps onto -4. So this is not a function. Not a function. Not a function. Now, does it have domain and range? Yes. Every relation has domain and range. Every function has domain and range. Okay? Because every relation has x and y. Because every relation is a set of ordered pairs. So domain and range, whether it's a relation, whether it's a function, yes, they have domain and range. Okay? Now, what is the domain here? Domain, you see, one good thing about doing this as a mapping is that once you do it as a mapping, you can easily find the domain and the range easily. The domain is a set of 7, -5, -3. Okay? The domain is a set of 7, -5, -3. And then the range is a set of -3, 4, -4, 2. That's it. Question 3. We have set of 4, 3, 3, 3, -3, 7. All right. Is this a function? Is this a relation? Yes. Is it a function? Yes, it is. No input repeats itself. 4, 3, -3. Yeah. No input repeats itself, so it's still a function. Okay? Now you might ask me, but these two inputs have one output. Yes. Okay? Yes. Is it possible for two inputs to have one output? Yes. Two people can work hard and still make the same grade. One person might, work a little, one person might work too much, but they still have the same result. It's still possible they can still make the same grade on the test. Okay? So, once there is exactly one output, the main thing about a function, the underlying thing about what is not a function is that the input will not have two different outputs. Two inputs can have the same output, but one input cannot have two different outputs. No. One input having two different outputs, it is a relation, but it is not a function. Okay? One x value cannot have two y values. Okay? One element cannot have two images, but two elements can have the same image. Okay? So, if you want to do it, if you want to map it, this will be 4, 3, -3, and this will be 3, 7. If you want to map it, x onto y. Now, 4 has an image 3, 3 has an image 3, and -3 has an image 7. Or image of 4 is 3, image of 3 is 3, image of -3 is 7. So the domain will be a set of, 4, 3, -3, and then the range will be a set of 3, 7. That's it. Okay? The range is a set of 3, 7. That's one thing I do that is in mapping. Once you map it, you can easily find that. Now, don't come here and write 3, 3, 7. No. Don't come here and write 3 twice. Don't do that. We don't do that, okay? Now, question 4 has this. It already has mapping. Words map to number. Okay? And here I have Sam, I have Dom, I have Man. Sam Dom Man. Sam Dom for peace. That's my nickname. Sam Dom for peace. Dom for peace. And then here I have mapping of 2. I have the images here. 2, 3, 4, 5. Okay. How many letters here? Number of letters. Number of letters. Put this as number of letters. Okay? So Sam has 3. Dom has 3. Right? Mark has 4. And then you ask yourself, is this a relation? Is it a function? You ask yourself that. Because you have 2 elements in the codomain. 2 elements that are not images. Right? 2 elements that are not images. So is this still a function? And the answer is yes. Look, if we represent it as this, other pair, this will be Sam 3, comma, Dom 3, comma, Mark 4. Okay. Provided that every input has exactly one output, and that no input has 2 different outputs, it is a function. It does not matter if some elements are not images. It does not matter. Okay? We are not concerned about whether these guys are images of elements of the domain. No, we are not. So 2 and 5, they are not images. That's fine. Provided that the elements have unique images in the codomain, you know. Now, the codomain is a set of all these, 2, 3, 4, 5. But the range is just a set of the images. The range is just a set of the images. Okay? So, it still doesn't matter. This is still a function. It is a relation. It is a function. Right? Because each element has a unique image. I know that Sam and Dom has the same image. It does not matter. Okay? Provided that there's no element that has 2 different images. Right? So the domain here will be Sam, comma, Dom, comma, Mark. Right? And then the range will not be all of them. The range will only be what? 3 and 4. Only 3 and 4. 2 and 5 are not included. No. Question 5, we have Congress, Mark 2, teamwork. Collaboration, you know, I would have said collaboration, not teamwork. Collaboration. Okay, here we have Democrat, Republican, Independent. Guess what we have here? We just have one thing here, just one image here. Guess what we have? 0. And this map to this map to this map to this. There has never, they cannot collaborate. It is funny to see how in schools, right, we learn ethics, work ethics. And if the work ethics we learn productivity, punctuality, collaboration, teamwork, right? And those are the work ethics we learn in school. But it's not practical. It's not practical in the Congress. They can never work together. Nothing is moving. Right now, it is just America being in default of its debts because they want to defund Obamacare. They will always find something to argue. Collaboration, 0. So this is a good example of what is happening on Capitol Hill. Pay them money to do nothing. Just sit down, argue, nothing. It's kind of funny to see. The House will pass a bill, right? The House will pass a bill, and on entering the Senate, it is dead on arrival. Dead on arrival in the Senate. The Senate will pass a bill, On entering the house, it is then on arrival in the house. Then what is the need? What is the need? Zero collaboration. See, and in the university, workplaces, we always learn collaboration. Collaborate. That is what gets things moving. Productivity moves when there is collaboration. You know, you think of all the things you learned as work ethics as a student in college. Come to work here. Then zero collaboration. Arguments. Nothing gets done. Nothing gets passed. Don't be surprised. The high probability that there's going to be default because of zero collaboration. Anyway, let's get back to mathematics. You know, mathematics is in politics as well. It's not just mathematics. We kind of give examples, philosophy, cause and effect, statistics, response variable, predictor variables. Yeah. So politics, we also apply politics in mathematics. So what is the domain here? The domain will be Democrat, Republican, Independent. That is the domain. And then the range will be, zero. Zero, 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 zero. All right, please, I hope you understood this topic. Watch out for part 2. Part 2, we will do more calculations, like more brain work in finding domain and range from equations. Here we found domain and range from mapping, and also domain and range from a set of ordered pairs. All right, thank you so much for listening to this video presentation. Watch out for other videos, and you have a good